This is the last video for the 9.2 and 19.1 series. This is still HL materials, it's 19.1. So now that we've talked about electrolytic cells and what electrolysis looks like and what's going to be discharged, there are factors that affect the amount of production in an electrolytic cell. And the amount of production depends on the quantity of electric charge being supplied, and then the stoichiometry of the half reactions that are occurring at each of the electrodes. So we can quantify, or we need to quantify, the electric charge so that we understand what's going on there. So as we saw several videos ago, that charge equals current times time. And so looking at the equation, Q equals I times T, or you can use the units, C equals A times S. Remember, we have Faraday's constant here, where 1 mole of electrons equals 96,500 coulombs. All right? And so that's what we're going to be referring to because it's an easier number in which to work with. Then we can go through and determine the amount of product from a redox reaction. So here's the setup, and so this is taking a calculation at a time. So we first need to know how much current and how long we're running that reaction. So this is going to be your C equals A times S calculation. That is going to give you charge. Okay, so once you know charge, which is C, we need to go to moles. This is using Faraday's constant, which equals C, which is your coulombs that you calculated previously, divided by Faraday's constant of 96,500 coulombs. And that is going to give you how many moles of electrons are present. And so that's looking at Faraday's. Once we know how many moles of electrons are present, we can go into the mole ratio of our stoichiometric equation. So there's that stoichiometry. That is going to give us how many moles of product, or whatever it is we're looking for. And so once we know the moles of product, we can then find the mass of the product. So mole, or M, equals moles times molar mass. And that's going to give you how much product we expect to earn. So we have our quantity of charge, right, to begin with. We have our stoichiometry. And with those two bits of information, we can predict the amount of product we're going to make. So now we're going to look at an example of how we can do a calculation to determine the amount of product of electrolysis. First, we need our problem. So from our problem, we know current. We're going to run 2 amps of electricity through our electrolytic cell. We're going to run those 2 amps for 15 minutes. How much copper are we going to get from the electrolysis of copper chloride? All right, we can do this. So the first thing we need to do, and the first step in the calculation, is find out current, right? So, or charge. So we're going to take CA, or C equals A times S, right? So A is current, so 2. S is time. We're running for 15 minutes, but we need to change that to seconds, so we multiply it by 60. And that's going to give us 1,800 coulombs. So now we need to know Faraday's. So what is that with moles of electrons? So we're going to take that 1,800 coulombs and divide it by Faraday's constant of 96,500 coulombs per mole. So coulombs cancels out, and we're going to get 0.01865 moles of electrons. Now, just so we know how many electrons we're working with, let's write this half reaction real quickly. So copper 2 plus is being reduced with 2 electrons to create copper solid. So amount of electrons to product, we have a 2-to-1 ratio. So that means we need to multiply by 1 mole of electron, or 1 mole of copper per 2 moles of electrons. So moles of electrons can cancel out. So 0.01865 divided by 2 is going to give us 0.00933 moles of copper. So now that we know moles of copper, right, we can find our mass of copper. So mass equals moles times molar mass. So we're going to take 0.00933 times the mass of copper, which is 63.55 grams per mole. And that means we're going to have 0.593 grams of copper released from 1 mole of copper chloride going through electrolysis. Another example is that we could do is, well, what if, just to show you how charge can affect it. So I'm going to do another example. So here we're working with a copper 2+, but copper is a transition metal, so it has the capability of having a different oxidation state. So what if we are working with copper +1? So it's only looking at a transition of 1 electron per copper. So it's a 1-to-1 ratio. All right? Everything up through Faraday's constant is the same. So, but the ratio is different. So that means we have 0.01865 moles of electrons. And that means for 1 mole of copper, we have 1 mole of electrons being discharged. So moles of electrons get canceled out. And then, so 0.01865 times 1 divided by 1 gives you 0.01865 moles of copper. Well, we can multiply that by 63.55 grams per mole. And we are going to get 1.19 grams of copper. So as you can see, depending on the amount of electrons that have to flow through the electrolytic cell, is going to give us a different amount of product. So having to discharge more electrons means we're going to get less product per time and current. Fewer electrons, more product over time and current. So charge on the ion influences the amount of product. Current running through, duration of electrolysis, all helps us predict what product and how much product we're going to get. So to look at a little bit closer of this charge of the ion and what effect it has, we are going to compare two different ions. Okay, so here we have sodium chloride. And then we're also going to compare it with lead bromide. So if we look at the cathode of each of these, so sodium has a single charge, so it only needs 1 electron to get reduced. Lead has a 2 charge, so an oxidation state of 2, and it needs 2 electrons to be reduced. So if you notice, we have a 1-to-1 ratio of sodium to electrons, and we have a 2-to-1 ratio of lead to electrons. So that means lead needs 2 times the electricity to produce 1 mole of product. So we need to understand what those half reactions look like at each of the electrodes. So let's look at an example of how we can look at some more variables. So in this next example, if we know current is 2 amps, time 10 minutes. And so we're going to run one example, and we realize that as we run this example of silver, we get 0.0124 moles of silver formed. What if we run current at 1 amp, but we decide to test time? So now we're going to run it for 30 minutes. What is the amount of silver produced? So this you can look at in a very simple manner of just looking at charge. Okay. okay? Because charge is an indirect measurement of amount of product. So we know charge. Let's say charge of reaction 1 equals amp1 times time 1 in reaction 1. This is very similar to like M1V1 equals M2V2. So we're running the same reaction again. So charge of reaction 2, ampage of 2, time of 2. The only thing we don't know is charge of the second reaction. So we can manipulate this to say, so the charge of the second reaction is the amps of the second reaction over the amps of the first reaction times time of the second reaction over time of the first reaction times charge of the first reaction. And we are saying charge is an indirect measurement of product, as we saw from the previous slide. It is a direct measurement or an indirect measurement. So let's plug in our information. So charge 2 equals 0.0124, which is C1, times 1.00 amps over 2.00 amps times 30 minutes over 10 minutes. And this is going to give us 0.0186 moles of silver. So now we can look at, well, the ratio and what we're changing and how much product we're going to get, and we can move that information forward. Now, let's say, well, we've been working with silver. What if we change it up? So we had silver above. Now we want to look at, well, let's look at copper. It has 2 electrons. This is a 1 to 2 mole ratio. So same problem as above, right? So saying we're making 0.0124 moles of copper, but now that we have 2 electrons instead of 1 electron. So an easy way to look at this is we take that 0.0186, right? Because that is how much, if we're looking at moles and we're just changing our charge and our time, or sorry, our current and our time, we get a certain number of moles of silver, but that's per electron. So then if we divide that by 2, because we have to take 2 electrons through, we get 0.0093 moles of copper. And we can see that it is half as much. Therefore, we would need to double everything else to try to make as much through. So again, showing you that charge, current, time, all affect production of the products in electrolysis. So depending on the information given to you, you can manipulate the calculations in different ways. Lastly, an application of electrolysis beyond rechargeable batteries, right? Beyond producing products like H2, Cl2, NaOH, H2SO4, products used in industry. This is yet another application. So what electroplating is, it is the process of using electrolysis to deposit a layer of metal on top of another metal or conductive substance. So what does the electrolytic cell need to look like for this process to occur? Well, the electrolyte needs to contain the wanted metal ions that need to be deposited. So if we're trying to plate something with nickel, that means the electrolyte needs to be made with nickel. The cathode needs to be made of the object to be plated. So if we're trying to plate silverware with silver, we need to actually have the fork, spoon, or knife submerged as the electrode into the electrolyte, in which the electrolyte has silver in it. And the anode needs to be made of the same material or same metal as that of the electrolyte so that the oxidation can create a replenishment for the electrolyte, as we saw with the copper sulfate example. So if we're trying to plate a fork with silver, that means the other electrode needs to be made up of silver so that we can move forward, or we have a continuous process. And so then we control, as we've noticed, current and time. If we can control those two things that affect the amount of product that are being produced, that controls the amount of thickness of the electroplating that's going to occur. So here's an example of the silverware, right? So we dip the fork into our electrolyte that contains silver, right? And then our electrode at our anode is made up of silver so that it can replace the silver in the electrolyte, continuing the process forward. The purpose for electroplating is for decorative purposes, like silverware, Corrosion control. So if you've ever heard of galvanized iron, so a lot of outdoor construction materials are going to be made of galvanized iron, which means we're going to use what's called sacrificial protection. So we're going to coat those nails, staples, everything in zinc. And the zinc is what's going to be eroded by water, protecting the structure of the iron in the construction materials. And then improvement of function. So we'll use like chromium to plate steel tools to allow the steel tools to last longer, fair weather, and stuff like that. So summary of everything we've talked about in 9.2 and 19.1. A voltaic cell converts chemical energy to electrical energy when the reaction has a positive E theta value, and it's going to go towards equilibrium. So it is a spontaneous reaction. An electrolytic cell converts electrical energy to chemical energy when the current drives the reaction with a negative E theta value away from equilibrium. So voltaic cells are like a battery. The electrolytic cell is taking that battery and recharging it and reversing the process that was run. That is the easiest way to relate it to each other. And then looking at what that E cell looks like and delta G. So in a voltaic cell, if the E theta value is greater than 0, so it's positive, right? That means the delta G is going to be less than 0, so it's going to be negative. We're going to have a spontaneous reaction. That is the definition of a voltaic cell. When our E theta cell is negative, so below 0, that causes our delta G to be positive, as we saw in the calculation of the Nernst equation. This is a non-spontaneous reaction, which means we now need to use an electric charge to push the reaction forward. At equilibrium, our E cell equals 0, our delta G equals 0. It's a dead cell, it's a dead battery. And so that means the voltaic cell has gone to completion, it's not hooked up to a charger, there's no use in it whatsoever. And that is the end of topic 9.